So right here is the shadow picture, where if I cast the shadow down, this much of this vector lands on it, right? So kind of the same direction. If I cast this shadow, none of it lands on it, so none of the same direction. Okay, what we're ultimately going to use these for, and the real value of dot products, is that we're going to be able to find them, use them to find angles. Now, if you hate this idea, the good news is if all the question says is find the angle between them, and you don't like this really short, easy process that we're about to work out, you could do the law of cosines instead. Like, this is just a much easier option than the law of cosines, but the law of cosines is still valid. So, yesterday we defined the dot product as this. If you give me two vectors and they're in component form, the dot of these things is just x of the first times x of the second plus the other product. So we're just multiplying stuff and adding it up, where this does not give us a new vector, and that's the weirdest part. So we started working out some properties or writing some properties yesterday, and this is our first one. What's the name of this property? If u dot v is the same as v dot u. Stuff can move or travel. It's the commutative property, so it stands. Nothing crazy there. Now, we're going to list these ones. There's only like 5 of them, but we do want to make sure that we get them all because this is a new operation for us. Okay, I'm going to switch colors for every single one. And I just want your gut feelings first. So here we go. What if I take the 0 vector, and I don't like that yellow, it's not very bright. What if instead I take the 0 vector, which is just what inside of my Insta brackets? 0, 0. What do you think happens if I dot a vector with the 0 vector? It should be 0, 0 again, right? Because it's 0 times something plus 0. Yeah, it's just the 0 vector again. Okay. Now, this is not like our true focus here. It's not the 0 vector. I misspoke. It's just 0 because it's a number. It's not a vector anymore. That's my bad. Erase the vector notation. Okay. This is an important idea. This may come back to be like an identity if you guys study this stuff further. All right, let's get another one. I just want to see your gut feeling. What if I had something like u, and I was trying to dot this vector u with the sum of 2 other vectors, like vector v plus vector w? You will not be wrong, I don't think. What? So I heard distribute. What was yours? And so what would I write if we were just distributing? U dot v plus u dot w.
Is the dot multiplication or is it not?
So I want you to think of it as multiplication, but we're not just multiplying vectors. So what you'll see eventually, and whether it's in this class or not, is, did you guys do matrices in Algebra 2 last year? Okay, so we're going to take a little side trip here for just a second. And if you don't remember doing matrices last year and you're watching the video, disregard. But I just want to connect this back. Addison's question was, is this just multiplication? I don't want to say yes, but I also don't want to say no. It's the dot product. Because if we have a vector that we normally write like this, 2, 3, you think I could possibly write it like this? Like, there's another way that I could represent it. And if from vectors last year, or matrices, you guys may remember doing stuff like this. And you're adding and multiplying and stuff like that they're in brackets and they're kind of ugly. It turns out this just kind of looks like a vector that I've written with AB or AC, depending on which way you want to write it. I'm going to write it as AC this time. And this kind of just looks like a different vector that we could call BD. Like, this is just another way to represent it. Maybe when you guys did matrices last year, it's just a bunch of vectors written together like this, and that's a new way to think about it. We're not doing crazy matrix stuff in here. But there is matrix multiplication, but there's other operations. There is the dot product. There's another one called the cross product, which is why I don't want to just say it's just multiplication. Yes, but it's the dot product. Don't just call it times. You'd say the word dot. Like, and I know it's weird, 5.3 or u dot v. That's how we're going to pronounce it. Great question. All right. Nothing crazy yet, right? 2 more. There's only one that I don't think will be obvious. What if I have some constant, c, as a scalar multiple, and I'm trying to scale up u dot v? Your gut won't be wrong. C u dot cv? Hey, it works. We can just factor out the constant. Ooh, yeah, cu dot cv. Awesome. Okay. We have one more, and we have 2 more because I wrote that one down wrong, and now I'm trying to think. I'm going to put a question mark next to this one just so I remember to look at it here in a minute. 2 more then. Okay, what if I have C? Am I wrong? I don't know. I'm not wrong. I'm just trying to figure out what I wrote. Ooh, we are wrong. We're going to change one little thing. We'll come back to this one. And I actually see Dolan erasing it already. We're going to make one little change. This would just be, if I think of it as multiplication, this C could apply to U or V. It would not distribute here. How come? Why does this not distribute like this? And I'm glad that
Oh, 'cause they're multiplying.
they're multiplying. I did not even cross my mind. Do we agree that it would not distribute? I don't care which one you erase. I'm going to erase that one. It's just C times U. Like you could do CU dot V or you could do U dot CV, but the C is not going to square. My bad on that. Sorry. Everybody erase the second C. Okay. Last one. And this one we're going to play around with. And I'm going to do some think over here and you guys are going to help me. What do you think happens if a vector dots itself? So square, kind of, right? But it's not just multiplying. Let's think of a nice little vector. We've not done a dot product yet. We're going to do one example together, and we can just work it through up here, and then you guys are going to be doing a bunch of dot products today. But let's just, give me a vector v. I don't care what it is. 5, 8. If I did 5, 8, and I dotted 5, 8, and you guys don't have to do this in your notes yet, because we'll do a bunch of these, we have a rule for the dot product. It's right here. How would this dot? So 5 times 5 would give me 25 plus 64. And it looks like, 99. Is that true? 89. Good. So no, it was not true because it's 89. Does that seem crazy hard? Now, this is going to seem arbitrary here, but do me one quick favor. Find me this. And how do we do this? So kind of the distance. So the square root of, there's easier choices here. 5 squared? 8 squared. Because it's just, from the rule yesterday, it's a, b is our vector. The magnitude of it is just a squared plus b squared, take the square root. What do we get? Huh. Well, those are almost the same. It's like we can maybe just take a shortcut if we ever have to dot itself. V dot V. Now, there's a whole bunch of different ways we can write it, but I want to try to connect this. These are almost the same. It's not quite just the magnitude of V, but it's really close. If I have the magnitude of V, what do I have to do to get to this? Boom. Not square root. Square. There it is. If you dot a vector to itself, it's just a square of the magnitude. And we saw it worked out right here as not really a proof, but kind of as an explanation. Are you okay? Okay. You're good. You want a clipboard? Okay. Okay. These 5 properties feel all right. Now, we need to know they exist. I'm going to do something different this year. Instead of just making you guys do a bunch of dot products right here, because of what we're about to see, is going to use the dot product. And it's a easy operation, I hope. Does anybody look at the dot? I just erased it. But did anybody look at the dot product that we did in pink up there and think, oh my God, that's so hard? You can multiply, you can add, you can do both. Okay, so we're going to actually just use the dot product, like right off the bat. So let's do that. Second little part. We're going to get one quick-ish definition, and then you guys will be up at the board. You'll have a lot of time to work today. Cool. The whole big deal about dot products and how we're going to use this anyway, and there's more to it than this, is oftentimes if we're working with vectors, we care about the angles between those vectors. Okay. Now, we will look at this, and I think I want to do one, we'll see if we do one problem together first or not. But we'll come back and we'll certainly talk about this stuff. Let's just get this down. If you have angles, can I draw a picture instead? Okay, because the wordy version is if theta is the angle between 2 non-zero vectors, then this is true. But I think we can just draw it. We can do the wordy version as well if we need to. So let's say we have 2 vectors. Let's say it's u, and I'm going to go downward here very intentionally. And let's say here is a different vector, v. Is there an angle between these vectors? Now, decision time. Okay, I'm going to give two colors. Don't draw them both. Nobody in here is colorblind, I don't think. Is it the green angle that's between them? Or is it the red angle that's between them? Everybody agree red. Could you convince me? What if I said, I think it's green, and I'm wrong, just so you know. How could you convince me it's red instead of green?
Between them, it's like the side of them. But it's, I don't know.
And like, I think I could tweak that argument, though, a little bit, right? Like, what if you came up here instead? What if that was you? Now it switched to here, I assume. Okay, so
Smaller angle?
easier way. So we won't even think smaller or bigger. At the start of class, I just made a comment. You didn't write it down. I said, we're going to learn how we use dot product to find the angle, and we're getting to that point now. But if you don't like it, you could use which method? You could use the law of cosines, which works for what shape? A triangle. Is there a triangle just waiting to be completed here?
Yeah.
It's this triangle, right? This is the only option for theta. Like, it's not that it's inside or outside, because that language can be misleading. The fact that it's the angle that forms on the triangle that it makes. That's what we after. Okay, so I'm going to label this theta. Okay, as long as these aren't zero vectors, which they're not, we're good. So here it is. It turns out, and I'm just going to give you a rule here, which I don't always love to do, but so be it. Turns out that if we want this theta, the cosine of theta is easy to calculate, easy to do, much harder to say than it is to do. All we have to do to calculate this angle, if you don't want to use a lot of cosines, is we're going to find their dot product, u dot v, in the numerator. And we are going to divide this bad boy by each of the magnitudes, or the product of the magnitudes, which this is ugly, but we'll just divide by the magnitude of u times the magnitude of v. Where theta is in radians. That's it. U dot v over mag u mag v is how I say that. Is this easier, you think, than the law of cosines? I guess we'll find out. We'll see. Okay, these comments, if you need them, because people keep getting a little bit goofed up. A couple things. If you give me a vector v, and we're just going to write these. You already have this, but I just want to re-emphasize this. That is a comma b. How do you find the magnitude of v? And I know Dolan knows, so somebody other than Dolan. Not that I don't want that answer. The square root of what? A squared plus b squared. So we've been using that. What if I wanted the theta for that vector v, which is, I use subscript to denote my stuff. Other books and online places might do it a little bit differently. But is this clear that it's the angle with this vector? I hope it is. How do you find this? So I'm going to draw one up here. Let's say this is the origin, and you don't have to draw it. I just want to think about it. Let's say that this is my vector v, and it's gone over how far according to this? A, and we know that number, and it's gone up b. Do we all agree? How would you find this angle? Which trig function? Opposite and adjacent, it'd be tangent, and then if you wanted to solve the theta, you would just do arctan. Now, for this is for in general with vectors, for one vector, right? Here's the angle of one vector. And there are roundabout ways that we could do this, where we could just find this angle right here, and we could find this angle right here, and then we could do the geometry to work it out. We could. But maybe we don't have to. Okay. This, if there's ever anything that I want you to internalize, this is certainly one of them. Cool. Well, based on your energy, I think we need to do some problems. Cool. 3, 6, 8 people. 2 groups of 3 and a group of 2, where I will chime in and help with your group of 3. Do you want me to pick them? Okay. Lots of energy in here. You guys glad it's Thursday or what? What am I looking for? Groups. Weird.
Right there.
Is it already open somewhere?
No, but you have like a shortcut for it.
Oh, yeah, that's... Yeah. Hey, I haven't done this since yesterday, so you guys are still highlighted, but we got to get rid of some people here. All right, so let's see. Weisha, you're here. Karina, she not. And Basil, she gone. Casey, she gone. And Matilda. All right. You guys would really rather do this and just pick your own groups?
There's my name crossed out.
I'm sorry?
Just kidding. I don't have my contacts in. It looks like there's a line through President's name.
If I knew how to do it, I would. Vamos! I'll get a problem up on the board for you. Rather than, I would encourage you'll probably want to add one of these into your notes at the end. But remember the rules, because other groups, I'm starting to be lazy about it, but I want to reemphasize. Who should not speak in this process? Whoever's writing stuff, right? Now, I just want to specify, you shouldn't speak about the math. If you have a comment, like you just need them to repeat something, you're allowed to speak. I just don't want you to get up there and talk through the whole problem. You're only writing what your other groupmate tells you. Okay. So for this, our first example, and we'll do a couple of these. I want you to find the angle between, please don't push my stuff. I'm messing with you, but that's fine. Okay, let's try it out. I want you to find the angle between, on A, we'll do vector u is defined to be the lovely vector 2, 1. And V will define as the lovely vector 1, 3. I want you guys to find me the angle between those vectors. Cool. We're going to do the last one together as a group. And if you want to put these ones in there, you're cool. You guys did the okay numbers. Is that easier or harder than the law of cosines? Easier. It's so fast. Now, there's something special that happens here. And we're going to observe that. But then we're also going to see that maybe we have a shortcut and we get one new word as well. Okay, let's work this one out. If I'm trying to find the angle between these, I know that cosine of theta, and here's my challenge without just immediately jumping to the notes. We're only doing C here because you guys did the other ones on the board. Cosine of theta is equal, I would put it in your notes, is equal to what? Like, how do I calculate cos theta? Just the general formula. I don't want you to say times. Dot u dot v over mag u times, and this is where it gets weird. If I'm never, like, obviously I won't be able to know if you're thinking dot or times. Miss Sweet question, because Miss Sweet likes linear algebra, which is what we're doing more than I do. If somebody says times, do you think it's okay instead of dot? No. Good. I'm glad we're on the same page. Sweet. Cool. All right. So check it out. Let's just work this one out. I don't remember how to do the dot product, which is kind of embarrassing. How do we do u dot v? I'm just going to do each part separately. Okay, I heard 6 whispered confidently. Times what? Negative 1/3 plus. Is everybody okay with this is u1 v1 plus u2 v2? Yeah. Okay, so let's just go one step further. What's 1/3 of 6 and made negative? Negative 2 plus, what's 1/5 of 10? 2. What's the dot product here? 0. Okay, now let's just think this out for just a second. No matter what the denominator is, my next line, and I know these don't have magnitude of 0, so the only thing the denominator can't be is 0, and it won't be because neither of those have length of 0. Are you okay with that logic? Neither of those vectors has a length of 0. Okay, so when I'm thinking this problem out, normally on A and B, you guys did magnitude of U and magnitude of V. Maybe we don't care right now, and I want you to make sure you can tell me why. We agree the numerator is 0. Why do I not care what mag U times mag V is? Is there anywhere on the unit circle where the cosine is 0? Where? 90 degrees. Now, all of a sudden, we're relating back to that thing we saw yesterday. If the dot product is 0, it means that, back to the picture, and I'm just going to scroll up. Here's the dot product being 0 situation, right? Like this is, none of this would go in the same direction. There's one more situation we should probably at least talk about. But this is 90 degrees, I think. Is this also 90 degrees? Like it has to be. There's no other option. So what we're going to say here, right off the bat, theta is just 90 degrees. Or how many radians? Pi halves. But there's an even bigger piece that we're going to generalize. Now, perpendicular has a meaning. What does perpendicular mean? Does it mean 4 right angles? Or does it just mean at least 1 right angle? Now, if there's at least 1, there's probably going to be 2. Because check it out. Can I put this pencil perpendicular to my table? Right there, right? Okay. Now, we are in 2 dimensions in that situation. Most of the world and everything that we do with mathematics really doesn't happen in 2 dimensions most of the time. If I have a line and another line or a segment, however you want to, I'm just going to say lines. If 2 lines form a 90-degree angle, we'd say it's perpendicular. It's a right angle, it's 90 degrees. That's what it means. Okay, do you think I can be perpendicular to something that's not a flat surface? Okay, is it this? Is this perpendicular right now? So your gut says no, and I'm not trying to trick you. We hold this pen. Put this on the surface, not in a way that you think is perpendicular. I don't know that we've gotten any more perpendicular. How come now? Just out of curiosity. So that's okay. Just forget about this. Pretend it's a flat surface. Like imagine this is a flat top. How would you draw it perpendicular to that flat surface on top? Do you guys agree that just straight out from the center is what we think of as being perpendicular? Do you also agree that it's weird to talk about perpendicular when we don't have lines to be perpendicular with? Okay, so it turns out there's a new word for it. You can think perpendicular, it forms a 90-degree angle, but because we could do the exact same thing with a 3-dimensional vector that instead of just being x, y, it goes out in space, we would get the same relationship. If we get a dot product that's 0, it means they don't go any in the same direction. But it can be weird to think about in perpendicularness. So we get a new word out of this. For these, we're going to sneak in a new word instead of perpendicular that we'll use with vectors. We're going to define orthogonal. Now, you guys all took, you guys did not take, you took Earth and Space Science, right? In middle school. With Mrs. Holloway or Miss Forfietta? Nope, probably Mrs. Holloway. Do you remember ever talking about maps with Mrs. Holloway? Maps. Like it'd be an earth science thing. Specifically, have you ever seen the maps where the lines, like they go and they get closer together when it's really steep or further apart when it's really like a topographic map?
Oh, yes.
Okay. Now, my guess is that you do not remember it, but I'm almost certain that when you guys were talking about maps and things like that and projections and whatnot, orthogonal projections probably came up. Now, you may not remember it, but if you've ever seen this word, that's a most likely place that it is. An orthographic map. All that this is 90 degrees to a surface. Now, if you use the word perpendicular, I get what you mean and you get what you mean. I'm going to let it slide, but I will always comment in probably a kind of mean way about it if you use perpendicular instead of orthogonal. 90 degrees to a surface. Is there an easy way that we can tell if something is orthogonal? Like the surface this time is just another vector, which is fine. How can we check? How do we know that this was 90 degrees without actually having to do the whole calculation? And check this out. We're going to make a claim and you're going to finish this. U is orthogonal to V if, and this isn't a theorem in our book, but I'm trying to think if this is an if and only if. Don't remember it if I'm wrong. If and only if feels pretty confident about this. what's true about the dot product? If you can show me that u dot v is 0, you know that those two things are orthogonal to each other, which means what angle? 90 degrees. Easy. Sweet. That's all I got for you. Cool. I lied. I have some homework. Feels okay? Awesome. So your homework, we'll call this 6.4. You will find waiting for you on page 437. Ooh, we'll have to talk about people absence and stuff here soon. We have one. Nope, we took out vocab. 7, 13, 15, 23, 31, 41, and 42. Okay. I'm going to pause this